Welcome to Pre-Calculus. Today we will investigate odd degree polynomial functions, focusing on graphing and analyzing for domain, range, and end behavior. We'll take a look at two examples. We'll begin with this first function, f of x equals x cubed minus 4x squared plus 6. So like we'd done when we were looking at even degree polynomial functions, we want to investigate here to see what's the degree of the polynomial. So just to remind about what is degree describing, it's really describing the highest power of x among the terms of the polynomial. So I'm going to look here at the powers on x here. In my function, I've got a power of 3, a power of 2, and if I consider this 6x to the power of 0, that would be a power of 0. So as I compare those three powers, the highest there is 3. So I would identify this as a degree 3 polynomial function. Now, in terms of what that tells me about the behavior of the function on the extreme left and the extreme right, that is an odd degree. The number 3 is an odd number, so it's an odd degree function, which means I've got one of two cases. I've got the left arm down and right arm up, or vice versa. In either case, one arm's going to be headed down, one arm's going to be headed up. So it's either left arm down, right arm up, or left arm up, right arm down. Now we can decide between the two of those possibilities by looking at the sign of the leading coefficient. So I notice here there's no coefficient on x cubed, so I'm going to record a 1. And what I'm going to notice is that is a positive leading coefficient. And so what that tells me is that the case that I'm looking at is that first instance. So I can narrow down my prediction to left arm down, right arm up. So we'll highlight that one. Left arm down, right arm up. And so as I look at the function and just consider what it might look like, it'll have this left arm approaching or traveling from negative infinity up, and then the right arm is headed up towards positive infinity. Well, let's decide about how that prediction goes by graphing with a table. So I'm going to put my domain column there. We'll choose -2, -1, 0, 1, and 2. And I'm going to calculate with the function. So again, I'm going to record this function in the right-hand column of the table. And let's get our values from Desmos. So I've written that one down. And let's input this into the graphing calculator and get some y values. So here I'm going to type in the function, which again is f of x equals 1x to the power of 3 minus 4x squared plus 6. So there's my function. I can see the graph there on the Desmos view, and it does essentially what we predicted. The left arm is going down, the right arm is headed up. There is a very kind of exaggerated curve in the middle. So I want to get a table, and looks pretty good. So I do notice that at -2, -18 is not really graphable. So like we do, I'm going to change the domain just to exclude that value, but I'll include -1, 1, definitely 0, 6. I notice that that's a kind of a high spot on the graph. That's a relative maximum. 1, 3 is there. 2, -2, but I see I need some more points because I don't have anything to describe that upward trend on the far right. So I'm going to enter to 3, -3, and then 4, 6. So I'll record those values. One point that I see that I need, because remember I need to record the extremes, I've got the maximum there at 0.6. I need the relative minimum. So on Desmos, I'm just going to go there, click, and I'm going to include that point, 2-point repeating 6, comma, negative 3.48. Let's graph. So I've got the information I need from the graphing calculator. I just want to fill in my table here. Let's adjust our domain. We had excluded -2, and we'd also included 2.6 repeating 3 and 4. So remember, you choose the domain values. You can put a guess there to begin, but then you can adjust it. So at -1, the output was 1.06, and we saw that was a relative maximum. 1.3, 2, -2, and then at 2-point repeating 6, we had a minimum at negative 3.48. And then to round out our table, we had the outputs at 3 of -3 and 4.6. So we're ready to graph. I'm going to get rid of the prediction there. And let's get something a little more precise. So -1, 1. Easy to graph there in quadrant 3, 0.6. Again, easy to graph as the y-intercept. Also my relative maximum, 1.3. 2, -2. Now this one, the next 2-point repeating 6, -3.48, I have to estimate that. And then at 3, -3, that's an exact value. And 4.6, back up into quadrant 1. And we're ready to sketch that curve. So the left arm is down. It travels up to the relative maximum at 6, turns back downward, relative minimum at 2-point repeating 6, -3.48, and then that right arm ascends into the high sky of quadrant 1. That completes our first task of graphing the function. All we want to do now is describe the domain and range and end behavior. So again, one thing we can do to help with both those tasks is to just see what's happening at the extreme left and the extreme right of the graph. So I'm circling those endpoints, which are really arrows. And I need to just kind of say what's happening in terms of the X and the Y direction at those two spots. So on the far left here, what I want to do is just say that this general trend of motion is down, but that graph is also drifting to the left. Similarly, at this upper spot, I do see that that general trend of the motion's up, but it's also drifting to the far right. So let's see how that helps write domain and range. So I'll start highlighting. Domain, remember, is a description of the X values. So where I'm looking for domain is the far left and the far right of the graph. And those are positive and negative infinity, but I'm also going to associate it with what I've said the left and the right side generally do for the function. So on the far left extreme, we've got negative infinity, and that's what that left arrow is saying. So my domain would start parentheses negative infinity. And then on the far right, that we would identify as positive infinity. And from my arrows, I see that that's where we're headed on that far right side. So again, this confirms what we've seen with polynomial functions, is that the domain in general is all real numbers. For the range, what we'd noticed with even degree functions was that there is some starting point or ending point, a relative or an absolute maximum or an absolute minimum. So I'm looking here at this example as well. Remember, range is a description of the y values. I don't appear to have any absolute maxes or absolute minima. So what I'm seeing, because this graph really travels uninterrupted from the lower part, here where I've got a one arm down, I do have kind of a squiggle there in the middle, but there's no interruption in terms of the function. The right arm is pointed up. And so what's different about odd degree polynomials is that the range, like the domain, is going to be all real numbers from negative infinity at the lower part of the graph to positive infinity at the upper part. And that's a big distinction between odd degree polynomial functions and even degree polynomial functions. We'll round out our analysis here by describing the end behavior. And where we'll lean are our arrow pairs that we drew to help with the domain and range. Remember, end behavior answers the question, what's happening to y? So I'll look at the lower pair of arrow hairs on the left, and I see there that all I got to do again is translate. So the horizontal arrow is pointing left. The way I would write that, as x approaches, left is negative infinity. The vertical arrow is pointing downward. So in terms of y would be approaching the downward direction is negative infinity. For the right-hand end behavior, I see the horizontal arrows pointing right. So as x approaches the right direction is positive infinity. The vertical arrow there is pointing up. Y is approaching up. We identify as positive infinity. So one thing we can see is that because we have an odd degree function with positive leading coefficient, we can check our prediction that we made at first with this end behavior analysis. The left arm is down, so y approaches negative infinity, and the right arm is up, y approaches positive infinity. So we can check our end behavior against our initial prediction. They should align with each other. They should match. Well, let's take a look at one other odd degree polynomial. So here we have negative x to the power of 5 plus 4x cubed minus 5x minus 1. We'll start with our predictions. So our predictions, again, are based on two things that we notice. So the first is the highest power of x. So we're looking for the degree. So I'm circling the powers here. I've got a power of 5, power of 3, power of 1. And then if I think that's x to the power of 0, power of 0. So the highest power there is 5. This is a degree 5 polynomial. So what I'll notice, again, is whether that degree is even or odd. The number 5 is an odd number, so this is an odd degree. So it's either got left arm down, right arm up, or vice versa, left arm up, right arm down. We can predict which one it's going to be by looking at the sign of the leading coefficient. So my leading coefficient here, again, isn't written as a number, but I do see a negative sign out front of x to the power of 5. So I'm going to put a negative 1. Negative 1 has a negative leading coefficient. So what I'll choose is this second option. So as I look at my graph, I believe just in general, it has some shape like that. Left arm up, right arm down. We'll confirm that with a table. So I don't really know what's happening in the center of the graph. My feeling is that there's some twists in there. Let's make our table and see. So left column x, and let's put -2, -1, 0, 1, and 2. I'm leaving that open for adjustments. So remember, the x values we choose, and we calculate our y values based on what we've chosen. So I'm going to put f of x for the calculation equals -1 x to the power of 5 plus 4x cubed minus 5x minus 1. I'm just putting that function there. So we'll need to populate that y column. Let's go to GeoGebra to do that, or Desmos. Why am I saying GeoGebra? That's another good free calculator, guys. The two main ones are Desmos and GeoGebra. So we'll use Desmos here. F of x equals -1 x to the power of 5 plus 4x to the power of 3 minus 5x minus 1. And there's my graph, so I can see the general trend of the prediction's good. That left arm is pointing up, the right arm is headed in a downward direction. And kind of like I expected, there's some squiggles, some curves in the middle. So I want to get a table of values so that we can plot that accurately. So I've got my standard 5 here, -2 through +2, and those look good. -2, 9 is not on this graph, but I can fit it on my coordinate plane. -1, 1, definitely graphable. 0, -1, that's our y-intercept. 1, -3, and then 2, -11 again is kind of low, but I can graph it. But what I need to catch from the table are the relative minima and relative maxima. I need to catch all the points at these valleys and mountain peaks. So the first one I see here on the left is -1.37, 0.39. So I need to add that to my table. Also, to the right of it, there's a peak, -0.73, 1.30. And then I've got two others that I need on this right side down in quadrant 4. So again, I'll click it there, 0.73, -3.3. And lastly, that last relative max at 1.37, -2.39. So like we do, I'm going to take the table and these 4 points. Notice those are not showing up in the table because the x values are not integers. Well, I've recorded that. Let's go back to our graph to get our function on the plane. We know that we got the general trend right. Let's make it better though with our y value. So I'm just going to record here first. So -2, 9. And then I need to write these values for x that we grabbed from the graph. So -1.37. In between -1 and 0, -0.73. We also had +0.73 and 1.37. We'll get the outputs then. So for this first -1.37, 0.39, -1 was at 1, -0.73 is 1.30, 0 is -1, that's my y-intercept. 0.73 is -3.30, 1 is -3, 1.37 is -2.39, and 2 is -11. Just want to notice that we would not have gotten those max and min values just from calculating on our own. That's something that the calculator really makes readily available. Well, we're ready to graph, so I need to include the value of 9. So -2, 9. -1.37 I need to estimate, and it's just above the x-axis at 0.39. So I'm going to estimate that's about right there. And then -1, 1. So I can see that's a relative minima there to the left of -1, 1. 0, 0.73, 1.30 is about there. So a relative maxima. 0, -1, that's my y-intercept. 0.73, negative 3.3. That I need to estimate. 1, negative 3, right there. That one's easy to graph. And then 2, before I go to 2, we got 1.37, negative 2.39. And then 2, negative 11. So that one I have to put extra marks, negative 9, negative 10, negative 11. So we want to graph this. So it's got the left arm that descends. Hits that relative minima, rebounds, relative maxima, back down to the y-intercept, a relative minimum, a relative maximum, and then descends forever. So we definitely got a good general trend from our prediction. We did need the graphing calculator to help decide what's happening in the center there. So we got a nice rough graph. Now we need to analyze for our 3 items here. So we're looking for domain, range, and end behavior. So domain is from the left to the right. To help me write that, I'm going to notice what's happening on the extremes of the graph. So I'm going to circle this upper arrow. That has a predominant travel up, but I see that it also drifts left. So in terms of domain, that drift left is going to begin at negative infinity. So we'll start writing that domain. Domain is from negative infinity. Now at the right part of the graph, I'll circle that arrow. The predominant travel is down, but there is a drift to the right, and that drift would head out to positive infinity. So the domain, again, is all real numbers. Now let's consider range. Range is, again, a description of the y values of the function. So from the lower part of the graph to the upper part of the graph. And where we're looking in terms of our arrows are our vertical arrows. So I'll highlight those. To write that, the lower part of the graph I see is headed downward. So that would begin at negative infinity. So our range begins negative infinity. And then there's no gap in the graph, and the far left side, again, is traveling up. I'm going to interpret that as approaching positive infinity. And that is very typical of odd degree polynomial functions. Both the domain and the range are all real numbers. Last consideration here is end behavior. And what we need to remember about end behavior is that we're looking at those arrow pairs again to describe what's happening to y. What's happening to y? And the way that I'll decide is by looking at these pairs of arrows we use to help decide about domain and range. So I got left arrow there. What I would say to describe that as x approaches the left direction's negative infinity. The vertical arrow there is pointing up, which is positive infinity. Y approaches positive infinity. And what that would go with is our initial prediction, left arm up. On the far right side, that arrow pair has the horizontal arrow pointing right. So I would translate as x approaches right direction is positive infinity. The vertical arrow is headed downward. Y approaches down direction, negative infinity. And what that would go with in terms of our initial prediction was right arm down. And that rounds out our graphing and analysis of odd powered functions, so odd degree polynomials. Thanks for joining. I'm going to let you graph and analyze your odd degree polynomials. See you soon.